Hello, this is Mohammad Ishtiaq Ahmed. I'll be giving a small lecture on diodes and diode rectifiers. In today's lecture, I'll be briefing on semiconductor materials leading to the construction of PN junction diode and their different biasing. Afterwards, we'll explore some of the examples of full wave and half wave rectifiers. The outcome of this study is to understand the concept of semiconductor diodes and to apply different biasing conditions in rectifier circuits to attain certain outputs. Let us start with some warm-ups. The first question that arises is that how the semiconductors are different than the typical materials around us. We know that the semiconductors have an inherent capability to conduct electricity under certain conditions. That means we have a grip on the conductivity of the materials, unlike the typical conductor around us. To elaborate on this concept, we may make a comparative discussion between the insulator, conductor, and semiconductors. We know that to conduct electricity through a material, there must be free electrons present in the conduction band. For an insulator, we can see that the electrons present in the valence band cannot jump to the conduction band due to the high band gap energy, more than around 5 electron volt. On the other hand, for conductors, we can see that there is a overlap between the valence band and the conduction band. This creates a greater ease for the electrons to jump from valence band to conduction band and to contribute in the electricity conduction. Now coming to the semiconductors, we can see that there exists a band gap energy in semiconductors. However, this band gap energy is way lesser than the one in insulator. We can make a comparison that for germanium, the band gap energy Eg is only 0.767 electron volt, whereas the one in insulator is greater than 5 electron volt. So typically a semiconductor material cannot conduct electricity because the electrons in valence band do not possess enough energy to overcome this band gap energy. However, if any external stimuli is provided, then the electrons in valence band absorbs the energy and they can jump from valence band to conduction band. And then the semiconductors became capable to conduct electricity. This is a visual representation of the electrons jumping to conduction band from valence band under the increasing effect of temperature. We can see that when the temperature arises, the electrons in valence band absorbs energy and they jump to the conduction band, leaving holes in the valence band. Now, these free electrons in the conduction band contribute to the conduction of electricity through this semiconductor. To have a greater control on the conductivity of such semiconductor materials, we adopt a technique that is called doping. Doping is simply adding some impurities in the semiconductor materials. For example, let's say we add a pentavalent atom in the silicon crystal. This will create one extra electron in the crystal, which will add to the conductivity. Again, if we add a trivalent atom in the silicon crystal, there will be one excess electron which can add to the conductivity. The first one is called the N-type material and the later one is called the P-type material. And the materials that have impurities added are called extrinsic materials. Now coming to the semiconductor diodes, a semiconductor diode is a two-terminal device designed to maintain an one-directional current flow. A diode can be formed by silicon, germanium, or other semiconductor compounds. So, a semiconductor diode typically has two portions. One is the P-type silicon part, commonly known as the anode, and the N-type silicon part, known as the cathode. This is the conventional electrical symbol for a PN junction diode. Now, this is the figure of the ion distribution in a common PN junction diode, inside a common PN junction diode. We can see that the contact surface of the p-type and the n-type, or maybe I can say the contact surface of the anode and cathode has a layer of ions, oppositely polarized ion there, preventing the transition of free electrons and holes from anode to cathode and vice versa. This layer of ions, oppositely charged ion, is known as the depletion region, and this forms the p-n junction. So simply, if I want to say, the p-n junction is basically the contact surface between the p-type portion and the n-type portion, and there exists a width of oppositely polarized ions that prohibits the transition of free charge carriers from one side to another side, resulting in a zero current through the diode. Again, in the second case, if we see that if we add an external voltage source in such a way that the anode is connected to the positive terminal of the voltage source and the cathode is connected to the negative terminal of the voltage source, the width of the depletion region has clearly reduced. You can see that here is the width of the depletion layer is larger than the width of the depletion layer in the second case. Why is it so? Because we have an external voltage source or an external force applied which matches the polarity of the p-n junction diode to the source. Now again, if we go to another case, the third one, we'll see that the depletion layer width has increased to a greater extent. Why that is so? We can see that now the negative terminal of the external source is connected to the anode and the positive terminal of the source is connected to the cathode. So we have simply inverted the polarity of the applied source. And we can see that the width of the depletion layer has increased to a greater extent, and this further prohibits the transition of the free charge carriers through the p-n junction. And we can see that in second case where there was a forward current, we would say ID. In the third case, there is no forward current. The direction of the current has changed. And I would like to mention that the magnitude of this current IS is way lesser than the one of ID. So here we could witness three cases where in the first case, the external source is 0 volt. In the second case, we are giving a positive external source, and in the last case, we are giving a negative external source. And in three cases, we could witness that the width of the depletion region is varying, and that is greatly affecting the transition of the free charge carrier, leading to the changes of current through this p-n junction. So here we term this second case as short circuit case. So if a p-n junction diode is connected to a positive voltage source, that means the positive terminal is connected to the anode and negative terminal is connected to the cathode, we refer this condition as a short circuit condition. And if the negative voltage is applied, that means if the negative terminal of the voltage is connected to the anode and positive terminal of the voltage is connected to the cathode, we term this condition as open circuit. So this will help us in understanding later concepts. So coming to the concept of biasing, what is biasing? Biasing is simply the thing we did here in the last slide. Biasing means applying external force. So here we are applying some external voltage source. This may be any other type of sources, anything. Applying any external force is known as biasing. So there can be three situations where VD or the voltage across the diode is zero, or the voltage across the diode is greater than zero, or the positive voltage. and the third one is a negative voltage. The first one is called as no bias condition, the second one is forward bias condition, and the third one is reverse bias condition. So let us recall that in forward bias condition, we term the condition as a short circuit condition. So their current flows through the PN junction, and in reverse bias condition, we term this as an open circuit condition where no significant current flows through the PN junction. Now, do you remember that while we were studying the formal definition of the semiconductor diodes, there was a point that a semiconductor diode is a two-terminal device designed to maintain an one-directional current flow. Now, what is an one-directional current flow? Let us elaborate. If we see this sine wave, this is also called the alternating current or the AC current. This type of signals have a positive portion in it, and a negative portion in it. So these type of signals have a positive cycle and a negative cycle. So this is called a two-directional voltage or current. And we can see that the resulting DC voltage is zero. But there are certain applications and appliances where we need the positive portion only or the negative portion only. In those cases, we need to cut down one of the phases, one of the cycles. So in this example, we can see that we are transforming this signal into only one directional signal where the negative cycle is absent. So this process is called the rectification process, where we make a two-directional signal made with a voltage signal or the current signal, we make it one directional. If I want to sum up, one directional means we are keeping only one cycle, either the positive one or the negative one. Now the circuit that performs this rectification process is known as the rectifier circuit. The rectifier circuits can easily be implemented using PN junction diode. How? Let us consider this example. Suppose we have an input signal Vi that has an amplitude of Vm. This is a period of 0 to t. Now we have a diode and a resistor connected, and we are taking the output across the resistor. Now, if we are applying this signal here, let's see. Now the positive terminal of the diode or the anode is connected to the positive terminal of the source for the positive cycle, right? For the positive cycle, the anode of the diode is receiving the positive voltage. So it will simply work in the forward bias, and in forward bias, the diode will be a short circuit if we are talking about an ideal diode. So the circuit will transform into like this. So you can see that the diode here has simply been short-circuited, right? So in the output, what will you get in the output? We'll get the same positive cycle. Right? Now consider the second case. For the negative half cycle, what is happening here? Let's say now we are applying the negative half cycle. For this negative half cycle, the anode of the diode is receiving the negative voltage. That means the diode has gone to the reverse bias condition. And in reverse bias condition, the diode will act as an open circuit. So in this case, the circuit will be like this. this is the open circuited diode, and this is the resistance. So for the time period T by 2 to T, there will be a break in the circuit. The circuit will be open. So here we'll get 0 voltage. So we'll not get any output here. Okay. Again, when this cycle is finished, another positive part will come up, and the diode again will be short circuited, and we will get here another positive voltage. So do you understand how these two directional signal has been transformed into this one directional signal? And now see, the average voltage or the DC voltage is not as 0 as previous. It has some values. Now the mentionable point is that we had a signal that had one positive half cycle and one negative half cycle. After the rectification process, we're getting only the positive half cycle, but not the negative half cycle. So 50% of the signal is cut off. We're getting only the 50% of the signal. Now, what if we want the 100% of the signal? That means we want the positive half too and the negative half too, but we don't want this half to be in the negative portion, right? So what can we do then? If we use this type of construction, let's say we have modified the previous circuit with this type of circuit. Now you can see that for this input signal, the time range of 0 to T by 2, the current will flow from here. And this T2 will be short circuited because this anode is matching the positive terminal of this signal. So this diode will be short circuited and the current will flow from through this resistor. And coming to there, this diode T3 will also be short circuited. So current will flow from this circuit to here and will reach here. So the path is basically here through the T2, through the resistor R, and through T3, and it will reach here. So here in the output, we'll get this portion. We'll get this portion. Now for the negative half cycle, what will happen? For the negative half cycle, our input is this from time T by 2 to time T. Now, unlike previous, T2 will not be in forward bias and so will not be a short circuit because now the anode will be receiving the negative voltage. But T1 will be in forward bias because this cathode is receiving the negative terminal. So now the path will change to this. Current will flow from here. Sorry. Current will flow from here. Then it will go through T4, it will go through R, and it will go through D1 and will reach here. So in simple terms, for the positive half cycle, that T2 and T3 will be in forward biasing, but T1 and T4 will be in reverse biased condition. For the negative half cycle, the diode T1 and T4 will be in forward biased condition, and the diode T2 and T3 will be in reverse biased condition. In both cases, you will see that the current is entering to the resistor from this terminal. So we'll get this output for the negative half cycle too. So previously we were getting this type of signal, and now we are getting this type of signal. So we have incorporated the negative half cycle too. So we are getting the 100% of our signal. So we could witness two type of rectification process. In the first type of rectification, where we are cutting off the negative half cycle, or I would rather say we are wasting the negative half of the input signal, it is called the half-wave rectifiers by half-wave rectification, because we are utilizing only the half portion of the signal, and the later case we are utilizing the two portions of the input signal. So this is called the full wave rectifications, and the circuit is called full wave rectifier. And you can compare in half wave rectification process, the average DC output was 0.318 pm, and in full wave rectification, the DC signal increases to 0.636 pm. Okay. Now this full wave rectification can be implemented using two types of circuit. This circuit is known as the bridge rectifier. Let me write it down. This is known as the bridge rectifier circuit. Now the same purpose can be served using this type of circuit. Now can you tell me what is the difference between these two circuits? Well, it's well evident that the bridge rectifier circuit has 4 diodes, and this type of circuit has only 2 diodes in it. We, the electrical engineers, always look for an efficient method and efficient setup where we can reduce cost. So here we are requiring 4 diodes, and here we require only 2 diodes. But in this setup, there is a transformer involved. This is called a center tapped transformer. Now let us explore how this circuit works. So we are giving the input here. So the positive half cycle, this diode is forward pass. This diode D1 is forward pass. So the signal is coming through this diode and then going through this resistor and reaching the negative terminal. But the diode D2 will be in reverse bias because the anode is connected to the negative terminal. Okay, so for the forward bias or the forward positive half cycle, we are getting this part of the signal. Now, if we think about the negative half cycle, we would see the terminals will be interchanged. So this will be positive, this will be negative, this will be positive, this will be negative. So you can see that in this scenario, diode D1 will be in reverse pass, but diode D2 will be in forward pass. So the current will flow through this diode, will flow through this resistor, and will reach this negative. In both cases, the current is flowing through the resistor and will get the output for the negative half cycle as it is. So let's compare. We got the same output, the bridge rectifier circuit and this type of transformer circuit. But the difference is the bridge rectifier circuit requires 4 diodes and this type of circuits require 2 diodes. Have you understood? These are the references I made these lectures from. You can see that if I shift this up, each section has been referred with the article number and reference book. So these are the reference books. You can explore these examples to have better understanding. And thank you for your time.